Hi guys, Nick Berry here from Seed Terminator. Today going to talk about the design intent behind the mechanical drive of the Seed Terminator. It's one of those things that we haven't spent a lot of time communicating. Our focus has really been on the mill technology because that's really where the major innovation occurs. Having said that, we've gone through a huge amount of development in the mechanical drive system from our first early days where we had a lot of issues in every component of the drive line, from the belts, gearboxes and bearing arrangements. And I guess, you know, the fundamentals of it have stayed the same, but we've basically redeveloped our thinking. So I guess in simple terms, so if we're looking at the back of the combine, the engine is typically faces east-west, and there is typically a gearbox on that side of the engine of the combine. And on most machines there's a pulley that comes off of that gearbox that we either adapt to take extra additional load or use what's on the machine. And it comes down to some kind of a jack shaft arrangement. So that's basically moving the belt drive inboard on the machine, and there's a belt down to the chopper, and or a belt down to our Terminator. The Terminator just takes that belt drive there onto a pulley, and there is simply a right-angled gearbox that is there. So we're literally converting the belts which are coming down the side of the machine from horizontal shafts to a vertical shaft, and then there is two belts across to some spindles which our twin mills are on. So the two mills, they spin in the same direction, and there's just two V-belt drives which drive each of them. And the reason we do it this way is because we take away, well, there's a few reasons here really. So there is a speed up to go from the gearbox to the spindle. So we keep the gearbox speed relatively low compared to the speed of the mills, roughly half the speed of the mills. So we're not stirring up oil in the gearbox, which is where most of the heat and wasted energy is generated. We also have the gearbox facing with the pinion gear facing down, so we always have oil on all the bearings. If you had the gearboxes facing the other way, then it's a bit more of a challenge. And what we're able to do with that slower speed gearbox facing this direction is that we don't have any external oil pumping or cooling. It is simply a change in direction, and that gearbox runs not relatively cool. So our typical temperatures on say a 30-degree day would be around that 70-degree oil temperature mark, which we monitor in the cab. And the two spindles here are especially custom made bearing arrangements. So we've gone through a number of iterations and lab testing, and then also 81 machines operating in the field last year and 32 the year before to really prove that system. They've actually got temperature monitors on them as well, so that we know that if a bearing is on its way out, we can start to pick it up. But the key thing here is that these bearings are really robust, and basically anything that's happening in those mills is supported by those bearings and not by the gearbox out here, which is potentially a more fragile component. So we're seeing that the bearing is taking any of the shock load or the vibration from these mills. The other thing is that the two mills are independent, so they're away from the load of the other one. So if something was happening with this mill, then it wasn't going to affect this one. But from there, the load back to here has that flexibility of the belt. So we've got a little bit of ability to slip, or we'll basically just reduce the transmission of vibration and load from here back to here. And the other cool thing about the way this is set up is that, you know, you can dismantle and replace mill components individually from each of them. They come balanced as a set, and you can just drop them in here, 20 minutes, you're up and going again, which is great. I guess having them spin the same direction has the potential to have some issues with spread, because you know, you've got one like this and it wants to spin that way, and then this one here, it's spinning the same way. But what we find is that the airflow from the mills is actually enough to really draw material from the harvester cleaning shoe, not affect the harvester cleaning shoe. We've proven that. But then also on the back side of it is spread it really well. So we have these chute extensions on this side, so it's a bit of a curved shape like that on this side. It means that they look a little different from left to right, but we are finding that we can spread it really evenly and draw that material in. And I guess the other part about having them side to side like this is that the feed of material, you know, we're not moving the chaff very far into those mills. We're just simply going from the full width, so something like 750 mil on each side, down to a 350 mil diameter hole, drawing that material in. We're not moving the material away from its natural flow. We're not affecting the airflow coming off of the sieve. It wants to go into the hole and be drawn in and spread. So, and that's basically the reason that we operate in this configuration. We really believe in this configuration. We've got a huge number of runs on the board with it.